Section: Introduction. In this section, we discuss the significant advancements in large language models, LLMs, over recent years, primarily driven by increased computational resources for training, larger models, extensive pre-training datasets, and improved alignment techniques. Recently, there has been a focus on enhancing task performance during inference by scaling computation, such as increasing the time the model spends thinking and using repeated sampling. This approach allows smaller models to perform similarly to larger ones by utilizing more computational resources during inference, enabling self-improvement with minimal human input. We note that while there are reviews on inference methods, there hasn't been a thorough examination of self-improvement at this stage. Our survey aims to fill this gap by categorizing existing literature and presenting the first taxonomy of these methods. We introduce the concept of LLM Inference-Time self-improvement, ITSI, which relies on the model's fixed parameters to enhance performance and efficiency without further training. These methods often use specialized decoding algorithms to refine the selection of the next token by adjusting the model's raw outputs and the probability distribution. We classify these self-improvement methods into three categories: independent self-improvement, which functions on its own; context-aware self-improvement, which utilizes external context and data retrieval; and model-aided self-improvement, which collaborates with other models. Our review draws from high-quality papers from leading conferences and highlights key challenges and future research directions. In independent self-improvement, we achieve performance enhancements using the model's own parameters without additional training. This includes modifying the decoding process, increasing efficiency, sampling multiple outputs, and isolating specific layers or neurons. We also explore constrained decoding, which directs the generation process through hard or soft constraints. Hard constraints are strict rules that must be followed, such as requiring certain words in the output. We discuss methods like neurologic, which enhances neurologic decoding with look-ahead heuristics, and control DAG, which allows for various controls to ensure the output meets specific criteria. Soft constraints, on the other hand, are more flexible guidelines that the model aims to follow while still focusing on fluency and relevance. We mention techniques like penalty decoding, which adjusts the probability distribution to discourage repetition, and IPS, which modifies token selection based on similarity to previous responses. Section Summary. In this section, we discuss the significant advancements in large language models, LLMs, driven by increased computational resources and innovative alignment techniques, highlighting the emerging focus on inference-time self-improvement methods. We categorize these methods into independent, context-aware, and model-aided self-improvement, emphasizing their potential to enhance performance and efficiency without additional training, while also addressing key challenges and future research directions. Section: Contrastive decoding. In this section, we discuss various decoding methods aimed at improving text generation. We introduce contrastive decoding, which modifies the probability of the next token based on differences in logits. To ensure faithfulness to the text, we propose PMI decode, which incorporates pointwise mutual information from the dialogue history. We also present LCD, which adjusts output probabilities using a dynamic weighting mechanism based on entropy. Next, we introduce anti-LM, a decoding objective that penalizes the next token's logits based solely on the test sentences, without considering other contexts. DOLA is another method we propose, which enhances factual accuracy by contrasting logits from different model layers. To address repetition and coherence, we suggest look-back decoding, which uses KL divergence to prevent token repetition and abrupt topic shifts. We also propose adaptive decoding, which adjusts the candidate's set size dynamically based on confidence levels. For minimum Bayes risk decoding, we differentiate it from map decoding by selecting the output that maximizes expected utility across translation hypotheses. We introduce DMBR, which adds a diversity penalty, and KMBR, which treats decoding as a clustering problem. CBMBR accelerates MBR decoding by clustering reference translations and using centroids for utility calculations. In terms of matrix approximation, we propose PMBR, which utilizes the low-rank structure of the MBR matrix for efficient score estimation. We also present pruning MBR to speed up traditional MBR by eliminating low-utility hypotheses and AMBR, which optimizes resource allocation based on computational budgets. For parallel decoding, we generate multiple tokens at once for faster results. We propose HGJ for machine translation, which combines Jacobi and Gauss-Seidel methods for quick inference. Arithmetic sampling generates diverse samples from LLMs, while LOOKAHEAD decoding speeds up the process by generating and verifying n-grams simultaneously. SOT creates an answer outline and fills in details through batch decoding. In sampling-based decoding, we introduce randomness for diverse text generation. BAT sampling applies constraints to discard higher probability tokens while retaining lower probability, higher quality ones. DMIN optimizes decoding by aligning sampled texts with human-like texts through a sampling importance resampling process. For reasoning, we propose self-consistency, which enhances chain-of-thought prompting by sampling multiple reasoning paths and selecting the most consistent answer. ESC improves efficiency by segmenting samples and stopping when answers converge. Lastly, we introduce ASAP, an adaptive sampling algorithm that ensures grammatical output while refining predictions iteratively. Section Summary. In this section, we explore various decoding methods aimed at improving text generation, including PMI decode for faithfulness, language contrastive decoding for probability adjustment, and minimum Bayes risk decoding for maximizing expected utility. We also discuss parallel decoding techniques for faster generation, sampling-based methods for diversity, and reasoning enhancements like self-consistency to refine outputs through multiple reasoning paths. Section: Tree Search-Based Decoding. In this section, we explore tree search-based decoding methods. We note that planning algorithms, like Monte Carlo tree search, MCTS, help us find the best text outputs for various tasks. For instance, we introduce PGTD, a model-agnostic algorithm that improves code generation by using an MCTS-like planning approach for look-ahead search without needing knowledge of program grammar. We also present GDP0, which encourages a large language model, LLM, to simulate dialogue interactions at each step of an open-loop MCTS. Additionally, we discuss RAP, where the LLM interacts with a world model, essentially the same LLM simulating the environment through specific prompts, and engages in planning using MCTS with potential actions from this world model. Next, we look at model-level decoding methods that function within the model's intermediate layers. We introduce ACD, which uses an early exit setup to compare probability distributions from an earlier layer, anti-expert, and a later layer, expert. We also present self-speculative decoding, which employs a single LLM for both drafting and verification. By selectively skipping intermediate layers through Bayesian optimization, we can generate draft tokens efficiently and verify them in a single forward pass. To improve factual accuracy, we propose SLED, which refines the logits using latent knowledge from earlier layers by minimizing the difference in probability distributions. We also discuss language-specific neurons, which activate certain neurons during inference to increase the likelihood of generating specific languages, like French. Furthermore, we identify overthinking and false induction heads, analyzing where correct and incorrect classifications occur in a critical layer, allowing us to identify and remove problematic attention heads, thus reducing the accuracy gap with minimal impact on correct prompts. We then address context-aware self-improvement, which boosts performance using specialized prompt-based or retrieval-based techniques. In prompting, we utilize carefully designed prompts to enable few-shot or zero-shot learning without changing model parameters. We introduce COT prompting, which helps language models produce coherent reasoning steps leading to an answer, based on few-shot examples. We also present zero-shot COT prompting, which uses a two-step template, first prompting with, "Let's think step by step," to generate reasoning, followed by, "Therefore, the answer is," to extract the final answer. To enhance zero-shot COT, we propose ECHOPROMPT, which starts with rephrasing the query to, "Let's repeat the question and also think step by step." However, we evaluate zero-shot COT on harmful questions and stereotype benchmarks, finding it significantly increases the risk of harmful outputs across various prompts and models. For other tasks, we introduce DECODINGTRUST, a multitask evaluation suite focusing on trustworthiness for LLMs, particularly GPT models, covering aspects like toxicity and fairness. We also propose Generation Exploitation Attack, which examines system prompt strategies and decoding methods, including temperature and sampling techniques. Additionally, we present URIAL, which aligns base LLMs using in-context learning with a few curated examples and a designed system prompt. Lastly, we discuss disturbed prompt methods that use specialized prompts to compare the model's probability distributions with and without these prompts during decoding. We introduce ICD, which employs disturbance instructions as role prefixes to contrast distributions for reducing hallucinations. We also present CAD, which compares distributions with and without additional context that may contradict the model's prior knowledge. Furthermore, we propose ID, where we contrast distributions with and without noisy instructions. We introduce COIECD, an adaptive decoding strategy that addresses knowledge conflicts between the LLM's parametric knowledge and contextual knowledge in the input text, applying an information entropy constraint to adjust non-compliant tokens. For safety improvements, we propose ROSE, which contrasts outputs generated with a positive prompt against those with a negative prompt during decoding. Section Summary. In this section, we explore various decoding strategies that enhance language model performance, including tree search-based methods like PGTD and GDP0, model-level techniques such as ACD and self-speculative decoding, and context-aware approaches that utilize specialized prompts for reasoning and safety improvements. We also discuss disturbed prompt methods aimed at reducing hallucinations by contrasting model outputs with and without specific instructions or contextual information. Section: Retrieval-based. In this section, we discuss model-aided self-improvement, which boosts performance using an external model, often a smaller one, like an expert model, draft model, or reward model. Expert and anti-expert models provide probability distributions that help guide the decoding process. We introduce DEXPERTS, which combines a neutral model with expert and anti-expert models during decoding. We also present MIL decoding, which assigns toxicity probabilities to tokens and merges them with the language model's probabilities to create safer text. For machine translation, we propose PSGD, which uses special tokens to focus on specific parts of the text. Codec treats initial translations as drafts, allowing another model to refine them. LIBS ensures translations are in the correct language by integrating a language identification model into the search process. Codec also includes a method for translating high-resource data, comparing translations to optimize the best options. To enhance model alignment, we suggest MOD, which combines predictions from multiple models trained for different objectives. Transfer uses a baseline model to compute optimal values for a target reward. For other tasks, we introduce SAFEDECODING, which creates a probability distribution to prevent jailbreak attacks, and GD, which combines distributions from an LLM and grounded models for robotic tasks. Superposed decoding generates multiple drafts in one pass, while equilibrium ranking uses game theory for consensus planning. We focus on the draft model in speculative decoding, which speeds up inference by proposing multiple completions verified by a larger model. SPECTR uses an optimal transport algorithm for faster draft selection. GSD improves the acceptance rate of draft tokens by generating multiple hypotheses. SPECEXEC builds a draft cache tree for efficient validation, and Sequoia uses dynamic programming for optimal structures. We also explore speculative decoding theoretically through Markov chains and introduce SCD, which validates token accuracy using contrastive distributions. Additionally, we propose online speculative decoding, which updates draft models based on user data to enhance predictions. Finally, we present Glide and CAPE, which improve decoding speed by reusing cached information and leveraging confidence scores, respectively. Section Summary. In this section, we explore various model-aided self-improvement techniques that enhance performance through the integration of external models, such as expert and anti-expert models, to guide decoding processes, improve machine translation, and ensure safety in outputs. We also discuss methods like speculative decoding, which accelerates inference by using smaller draft models to generate and verify multiple completions efficiently. Section: Small LM, Amateur LM. In this section, we explore the use of small language models, also known as amateur LMs, alongside the draft model in speculative decoding to assist in generating outputs from larger language models. We utilize various classification models to guide this generation, including those for evaluation, adjusting probabilities, and replacing tokens. We introduce Neurologic A.P., which combines high-quality segments from the best hypotheses using a binary classification model to assess token quality, creating constraints for Neurologic A. We also present critic-driven decoding, which employs a text critic classifier to merge its output with the language model's probability distribution, adjusted by a scaling factor. Similarly, we propose KCTS, or knowledge-constrained tree search, which aligns generated outputs with reference knowledge by integrating a knowledge classifier score with Monte Carlo tree search. Here, the candidate generation acts as the tree's root, while other outputs are sampled through leaf nodes, where we evaluate factuality using a token-level knowledge metric. Next, we introduce ENDEC, or enforced decoding, which modifies LLMs with a conditionally activated decoding goal. This includes adding positive prefixes and replacing negative words with positive ones based on sentiment classification. We also propose CD, or contrastive decoding, which compares the probability distributions of a large expert model and a smaller amateur model, penalizing next tokens where the amateur model is confident, but only when the expert model lacks high confidence. We present BUILD, or Big Little Decoder, a framework that learns to use two models of different sizes collaboratively, where the small model generates text efficiently and the large model refines it occasionally. JAMDEC, or Jambalaya decoding, is our method for authorship obfuscation using small language models, which involves keyword extraction, overgeneration with lexical constraints, and filtering for stylistic distinctiveness. Our reward model, a fine-tuned language model, evaluates generated responses and assigns scores to guide the decoding process. We propose RAD, or Reward Augmented Decoding, which uses an external reward model to adjust logits with a steering factor. To enhance alignment, we introduce ARGS, or Alignment as Reward-Guided Search, which incorporates alignment into the decoding process, adjusting the model's probability distribution at each step. We also present TSLLM, or Tree Search Enhanced LLM, which combines deep tree search techniques with a learned value function and outcome reward model. Additionally, we propose CD, or Controlled Decoding, which employs a trained prefix scorer to guide generation from a fixed model. In terms of tool use and APIs, we discuss GCD, or Grammar-Constrained Decoding, which applies context-free grammars to enforce constraints through an incremental parser, eliminating non-compliant tokens. We introduce neurostructural decoding, which applies structural constraints to maintain subject-verb-object relationships, enhancing neurologic decoding by incorporating conjunctive normal form constraints. For code generation, we propose MGD, or Monitor-Guided Decoding, where a monitor queries a static analysis tool during the decoding process, integrating the output through a mask on the logits. Lastly, we present FLAP, or Flow Adhering Planning, for dialogue systems, which converts planning steps and API calls into dependency graphs that serve as constraints during decoding, enhanced by a look-ahead heuristic. Section Summary. In this section, we explore various methods for enhancing language model generation, including the use of small or amateur models for guiding outputs, classification models for token quality estimation, and reward models for adjusting probability distributions. We also discuss techniques like grammar-constrained decoding and structural constraints to ensure compliance with specific task requirements, alongside innovative approaches for integrating external tools and APIs into the decoding process. Section: Discussion. In this section, we explore the strengths and challenges of inference-time self-improvement methods. These methods enhance reasoning, ensure accurate generation, and boost speed through parallel processing, all without needing to change model parameters or undergo extra training. However, we still face several challenges. First, we need to consider maintenance. Methods that rely on external data or models require regular updates, while independent methods function solely through the decoding process and do not need this level of upkeep. Next, we look at model access. For instance, the OpenAI Chat API provides only a partial probability distribution, which means methods that depend on the complete distribution are not feasible. We also encounter trade-offs in inference costs. Techniques that increase inference time, like sampling multiple generations, typically take longer than those that directly adjust the decoding process. Generalizability is another concern. External models guiding the generation are often tailored to specific tasks, and adapting them to new contexts usually requires creating new expert models or fine-tuning existing ones. The performance of these methods heavily relies on the quality of the auxiliary models. When it comes to generation quality, methods that adjust the decoding process allow for real-time changes to meet specific conditions. However, these conditions can conflict with the language model's natural tendencies toward fluency and coherence, leading to a trade-off between enforcing constraints and maintaining quality. We also note the need for explainability and interpretability. Few studies have examined the decoding process of language models from the perspective of their internal components, presenting an opportunity for future research to enhance our understanding of how these models make decisions, especially in complex reasoning tasks. Due to space constraints, we cannot cover all methods in detail. Our focus is on key sources like ACL, EMNLP, NAACL, NeurIPS, ICLR, ICML, and archive from recent years. We aim to keep updating our online resource with new methods and datasets. We also address ethical considerations. Our review highlights significant ethical issues, particularly regarding social bias. Language models often show biases related to race, gender, and other social factors. Just as we need bias analysis and debiasing methods for base models and parameter-efficient methods, we must also apply these to self-improvement methods. For example, we find that certain techniques can increase harmful outputs, and including explicit mitigation instructions in prompts may help reduce these biases. Additionally, methods that use external data or models might introduce their own biases. Lastly, we consider economic equity. Language models can be expensive, leading to the phrase, GPU poor. Lightweight, inference-time methods like self-improvement could lower the costs of accessing these models, potentially promoting greater economic equity in both model-as-a-service and local hosting scenarios.